this is MESLIN'S modification of billets split lens interferometry. Here our normal lens is like this. We have split it into two portions, and then this lower portion is here from this place shifted to this place. So previously we displaced it vertically, now we have from here shifted this way. So this is MESLIN'S modifications. So this is how the lens has been split up. So we will see now, let us see that this is my point source S, and you see this is my wavefront. Now this wavefront is splitted into two portions, one due to this lens, and this wavefront forms a virtual image due to L1 as here, and due to L2, sorry, real image, this is at S2 is formed. So the wavefront from here passes, it converges here and then it diverges like this, and the wavefront from here converges at S1 and this then diverges like this. So this is the region where we get interference pattern. So this is the region where you see the wavefront from coming from the upper lens, you see it goes like this, and from the lower it goes like this. So this is the region where interference pattern is formed. So here only in this lower half, not this half, this in 3D, three-dimensional space, if we put a screen here, we will get curved type of fringes. So this is the region where interference is formed. Some students may get confused thinking that the interference pattern is formed this way. There are two sources and there you will get circular interference pattern, and they start calculating path difference on any point due to these sources. But that is absolutely wrong, because the interference is confined within this region. Here interference pattern is not formed. So that will be wrong. Interference pattern is here. We are not going to calculate path difference and fringe width and all such things. So this is how MESLIN'S modification has been done. This. Now let us see another type of arrangement somewhat similar to billets split lens, in which this is my lens. This is not MESLIN'S modification, another modification we are going to study. This is my lens, and now I have cut out this portion. This portion has been removed. I am going to remove this portion, and then I will put my lens here. That means this portion has been shifted here, this portion has been shifted here. So this portion shifts by d by 2, and from this point, this portion shifts by 2. So I have removed this portion and pasted these two portions of the lens to form a single lens. It's a single lens, but it's not a single lens. The individual parts behaves as own lenses with their own optic axis. So this we will see with these modifications how we will get the interference pattern. Okay. Now this is my lens, which was earlier a lens like this, and what I had done, it has a focal length f. This portion is removed. This portion has a width d. This has been removed, and now this upper half is brought here and this lower half is brought here. So my lens, this is this thing. That means already I have removed. So now this half has a optic axis d by 2 distance here, and this half has a optic axis d by 2 distance here. And I have placed a source at a distance a which is less than focal length also, so that I can see here how. So here I have done two modifications in my billets split lens interferometry. First of all, I didn't simply displaced it. I have cut that portion and brought these two lenses and pasted it like that. So, the optics axis is now lower than this line. Second, I am putting this source between pole and focus, so that here we will get a virtual image. So, first of all, with geometrical optics we have to calculate where will be the image formed. So, this is the total modification we have done. Now, let us first calculate with geometrical optics where is the image formed. So, this is my lens. Suppose I just consider the upper half. This is my object O, and you see here actually this is the optic axis of the lens. This is the optics axis of the lens, and this distance will be d by 2. Now, because of this lens, where is the image formed? So, suppose I consider a ray. This is the optical axis, so it passes undeviated. It will pass undeviated. And suppose this is the parallel ray, it will deviate. Any ray from here, it will deviate, and an image is formed here. So, an image is formed here. So, this will be S1. That means this source will form a virtual magnified image due to this upper portion of the lens. So, we have to first calculate what is this position V, and from magnification or even by similarity of triangles we can calculate, because this ray goes undeviated. So, if I draw this, so by similarity of triangles also we can calculate what is this distance. So, once I know this distance, S2 will be similar. So, 2 times that distance we can calculate. So, we will do by similarity. Let us calculate this distance. So, you see, this is my upper portion of the lens, this is the object. If I complete the whole lens, the optical center will be here, the whole optic axis has been shifted by d by 2. So, in order to locate the image of S1, what we will do? We will draw a line passing through O and the optical center of the actual lens, then it will go undeviated to somewhere here the image will be formed. So, this distance we are interested, and we have to also calculate this distance. Now, using lens formula, that is 1 by V minus 1 by U is equal to 1 by F. Here V is required, U is, suppose this distance is A given. So, A is negative, focal length is F, implies 1 by V is 1 by F minus 1 by A, that is equal to A minus A by AF. So, we have V is equal to AF by A minus F. V is negative. So, let us call this distance as B. So, the B is negative. So, we will write that B is FA by F minus A. You see, this A is less than F. So, let it be only this. So, this is V. This is F when A is less than F, V is negative. So, the value of B becomes, the magnitude of this distance becomes AF by F minus A. So, we got this B as this. because this A is less than F, this is positive, means this is magnitude we are writing. So, we got B which is equal to A F by F minus A. This is B equal to. Now, once I got this V, by simply geometrical optics we can calculate magnifications also, that this is D by 2. So, what is this distance? Simply by B by A, or you can calculate by this similarity of triangles also. So, anything, suppose I use magnification is equal to B by A, V by U is equal to H2 this by this. So, we will get magnification means here you see something, this is object. So, from here you will get a image. So, if this is the object, this is the image. So, you will get this, suppose I call this edge, this is O dash. So, that is this O dash S by this distance, that is D by 2. So, O dash S becomes BD by 2A. Now, B is this and D is already known, 2A. So, B is, we will put D by 2A times AF by F minus A. So, O dash S is equal to this A cancels, DF by 2 F minus A. This is O dash S, O dash S1, O dash S1. Now, O dash S1 we got, but actually we require this thing. So, this thing will be O dash S1 minus D by 2. Again I have to do this, and S1 S2, this is one image S1, there is another image of S2 formed from the lower halves, and that so S1 S2 will be 2 times S1 O dash minus D by 2. So, that is 2 times this distance is S1 S2. So, we will see S1 S2, that is interesting part. S1 O dash, that is D minus F by 2 times F minus A minus D by 2. Let us calculate this. So, if I bring 2 inside, it will be F minus A minus D, that is equal to F minus A, D minus F minus DF plus AF. So, now let us see by geometrical optics where is the image formed. This is L1, the portion above. You see, actually this is the actual optic axis of this, which is at a distance of D by 2. So, I have placed my object here, and you see this will form a image somewhere here. This will be S1. S1 will be the image. So, you just imagine this is the optic axis and this is my object distance A, and so this B will be the object distance this. Now, let us calculate first of all what will be B. This A is less than F. So, we have one length formula, using length formula 1 by V minus 1 by U is 1 by F. So, 1 by V is lying this side. So, let us call it B, and we know that is virtual. U is again plus 1 by A and F is F. So, implies 1 by B as 1 by A minus 1 by F, that is AF, F minus A. So, we have B is equal to AF by F minus A. So, we got this distance B. Now, using magnification, suppose I call it O dash O dash, let us call it, suppose I call it A and this is O, B. I call it A and B. So, magnification is equal to A S1 by this distance, that is equal to D by 2. This distance is D by 2, no special name. That is equal to V by U, that is again B by A. B by A implies A S1 is equal to B D by 2A. So, this is A S1, we got B D by 2A. Now, we require S1B. So, S1B will be equal to that whole A S1 minus, again this is D by 2. So, that is B D by 2A minus D by 2, that is equal to half common, D by 2 common, we have B by A minus 1. So, we have S1B as D by 2 B by A is itself F by F minus A and minus 1, that is D by 2 F minus F plus A by F minus A, that is equal to, this cancels out, D A by 2 F minus A. So, this is my axis and S1B is above the axis, S1 is at this distance. So, similarly there is S2 here because of the lower part. So, S1 S2 is 2 times SB. So, S1 S2 is 2 times S1B, that is equal to dA by F minus A. This is S1 S2. S1 S2 we got the distance between the two slates as dA by F minus A. This is the most important point which we have to calculate from geometrical optics, the location of the image edge S1 because of O due to upper half, because of lower half there will be an image S2 because of F. So, thus here we get two virtual sources of S1 and S2, that is dA by F minus A. These are the two virtual sources. In billets split lens we got these two S1 and S2 at here and they were real sources. These are virtual sources. So, now let us see how interference is formed. Okay. So, you see here, this is my lens which after cutting has been pasted. This is the source placed here. This source due to upper half has produced a virtual image S1. So, the rays after refraction forms at A1 B1. Similarly, the source S has formed a virtual image S2 this side. This is magnified image and this wavefront reaches into A2 B2 region. So, A2 B1, that hashed region has the interference pattern. We wish to calculate what is the total number of fringes formed here and what is the fringe width, for which I require the distance between S1 S2 which we have calculated earlier, and then let us calculate fringe width. Fringe width first. Fringe width is given by lambda d by d, that is lambda, here d means total distance between this, that is B plus L by d. D means this is here S1 S2, that is my d. So, here d means S1 S2, that is lambda. What is B? B is F. B means this distance that already calculated, that distance is F minus A, AF by F minus A, plus L upon S1 S2, which is already calculated as AD upon F minus A. So we have fringe width beta as lambda AF plus FL minus AL. This cancels by AD. This is our beta. This is the fringe width beta, and now let us see. This is beta. Okay. Now let us calculate the total number of fringes formed within this region. So for this, we have to again use similar triangles that this region. You see there are two triangles, this triangle and this triangle. So number of fringes can be calculated. First we will calculate A2 B1. Now by similar triangles, from the diagram you see this triangle is similar to this. This is opposite vertical angle, this is parallel to this. So these angles, so these two triangles are equiangular. So A2 B1 by similar triangles, A2 B1 by L is equal to S1 S2 by B, implies A2 B1 is L by B S1 S2. So let us calculate it. A2 B1 is L by S1 S2. S1 S2 is AD by B minus A by, this is L into B. B is AF by F minus A. This is B. This is B is AF by F minus A. And this S1 S2 already we have calculated is AD by F minus A. Sorry, this is F minus A, not B minus A. This is S1 S2 already we have calculated as AD by F minus A. So F minus A cancels. So this L AD by AF, that is LD by F. This is A2 B1. So I will write it better, LD by F. So I got this distance. So now we got this distance, we got this beta. So it is easy to now calculate the total number of fringes. So I am writing here. So total number of fringes N will be equal to LD by F, this distance, by beta. So I require the value of beta. So N will be equal to LD by F into beta. This value, that is itself lambda AF plus FL minus AL by AD. So this is what beta is required. So this will give, that is L AD square F lambda AF plus FL minus AL. This is our total number of fringes. This is total number of fringes. Now this function, if we study, this is LAD and F lambda AF plus FL minus L. So total number of fringes.